This is Unit 3.8, Human Population Dynamics. And if you haven't seen or read Soylent Green, then you know that it has a lot to do with food availability. It's kind of funny that it's set in the year 2022, right? We're not having the food problems that they describe in this movie, but yeah, this is an iconic movie, has Charlton Heston, and the big mystery is, what is Soylent Green made out of? So in population dynamics, right, we talked about growth rate, change in size over time, and this includes birth rates, death rates, immigration, individuals coming into a population, and then emigration, individuals leaving a population, and then growth rate also depends on life expectancy. If you're trying to remember emigration, and immigration, then maybe here's a good graphic to help you. So let's say you have a population of geese, brown geese and white geese, and over there you have a population of just brown geese. The white goose is going to emigrate from its current population and immigrate to its future population. So increasing population size can be due to births or immigration. Decreasing population size can be due to deaths or emigration. Within this, we have what's called the rule of 70, and this is a math shortcut and exists pretty much only in this class, AP Environmental Science. So let's say you take your population growth rate, let's say it's 4.5%, and you divide 70 by that population growth rate. Then the result is, in years, the approximate time for a population to double. So in the example I just gave you, right, if you take 70 and you divide it by 4.5, you get 15.55, kind of 5 repeating. So 15.5 years that it would take for a population to double at a growth rate of 4.5%. So if you want to do some math practice, we've got a bunch of equations for you to check out. We have things called the crude birth rate, which is number of births per 1,000 individuals per year, and the crude death rate, which is the number of deaths per 1,000 individuals per year. We know that population density is population divided by area. If you want to find a national growth rate, you're going to take your increasing population numbers, the crude birth rate and the immigration rate, and you subtract out the crude death rate and the emigration rate. You divide by 10 because all those numbers are in rates per 1,000. So then you get a rate that's divided by 100, and then you can get some percentages off that. Global growth rate, right? The R for the population of the entire Earth is the birth rate minus the death rate divided by 10. And that's because we're talking about the whole Earth. So there's no emigration or emigration. So the rule of 70, of course, is that the doubling time in years is equal to 70% divided by the growth rate in percentage. So again, like I said, 4.5%, divide that into 70, you get something like 15.5. So we're going to do practice with that in a minute. So you find future population from a growth rate using exponents, where you need the initial population and you take the growth rate, and then you take that to the power of the number of years. That'll give you a population. So for example, a growth rate of 3% is expressed as 1.03. So if you have 468,843 people times 1.03 to the 10th power, right? So 1.03 times 1.03, so on, 10 times, you would get 630,000 people after 10 years at a growth rate of 3%. So we're going to calculate some growth rates here. So you take the birth rate minus the death rate, and then you divide by 10, and that gives you a percentage. So for example, for the US, it's going to be 13 minus 8 divided by 10 is going to give you a rate of 0.5. So what you should do is pause the video here, calculate the rest of these, and then the growth rates, and then I'll click through and you can check all your answers. So for Mexico, it's going to be 19 minus 5 divided by 10, right? 1.4, negative 0.1 for Japan, 0.4, 0.5, 1.6, 2.5, 0.7, 0.4, negative 0.1. For the doubling time, you're going to take 70 and divide it by that growth rate. So the doubling time of the US population is going to be 140 years, right? When you divide 70 by 0.5. So pause the video, calculate the other doubling times by taking 70 divided by the growth rate. And after you've completed all of those, come back to the video, start it up, and check your answers. So for Mexico, it's 50. Japan, not applicable, right? Because they are shrinking. UK, 175 years, 140 years in China. India, a little under 44 years. Nigeria, only 28. South Africa, 100 years. Canada, 175 years. And then the same thing for Italy as Japan. No doubling. So what do the populations of different countries look like today? So we've got this diagram, or the circle corresponds to the size of the population. You can see China and India have the largest populations, and then plenty of other places, United States, Indonesia, Brazil, are following up close behind. You can also show this where it kind of shows like a map of the world relative to the population size. That's kind of helpful to look at. Or this one's kind of funky. You can see how much China and India have in terms of population here. So what are all these 7 billion people in the world, right? Most of them are too young to work. A bunch of work in services or agriculture. Some work industrial jobs. Plenty are retired, 577 million, though maybe not retired. They're just older than 64. Many are unemployed, and then some are entrepreneurs. So how did we get to this huge population size? So 400 years ago, we discovered like major forms of agriculture. Obviously, agriculture has been around for a while, but really 400 years ago, it really took off. We had improvements in sanitation and medicine. Right, we developed sewers so that we didn't just throw our refuse out of the window. So the question is, the Earth has a carrying capacity. Are we there yet? Some people say yes, and some people say no. So one option, have we exceeded the carrying capacity? It could be yes. And Malthus said this in 1798, that the human population is growing exponentially, but food production grows linearly. And so at some point, the population would outpace the production of food. Then we would have war, famine, and disease. And there are a lot of people who agree with this. But another option is that no, we've found ways to innovate and create solutions to our problems, increase our technology. And so as the number of people continues to increase, the supplies available to them increase as well. So you can come up with your own answer, yes or no. But there's a major problem is we don't even really know what the Earth's carrying capacity is. If you ask a number of experts to come up with estimates, you could see that some people say 8 billion, but the estimates are as low as 2 billion or maybe as high as over 1 trillion. So there's a lot of disagreement over what the carrying capacity is and whether we're at it or about to reach it within 10 or 15 years. All right, well, that's Unit 3.8. Please let me know if you have any questions.